Hello, are you hearing?
Yes, sir.
Right. Are you seeing the slides there?
Yes, sir. Yes, sir.
In last class, we finished viscosity and kinematic viscosity and two problems. Okay.
Okay, sir.
Uh, right now, let us discuss the compressibility and bulk modulus. Compressibility and bulk modulus. Please, anyone read the slide, please.
Compressibility and bulk modulus. Compressibility is the reciprocal of bulk modulus of elasticity, K, which is defined as the ratio of compressive stress to volumetric strain.
Fine. Okay. Right. Compressibility is the reciprocal of the bulk modulus of elasticity K, which is defined as the ratio of compressive stress to volumetric strain. Understand? So if we understand the compressive stress and the volumetric strain, then only we are able to understand the meaning of compressibility. So to understand all these two parameters, we are considering one cylinder fitted with a piston. Okay. Okay, you are seeing one cylinder. Okay, you are seeing one cylinder. Say cylinder is fitted with a piston. Okay, you just assume the piston is at this position, being it is a horizontal cylinder. This position is called outer dead center, and this is called inner dead center. Understand? When piston is in this outer dead center, let us assume cylinder is filled with gas with the volume of V. With the volume of V. Okay. That means cylinder is filled with gas of volume V and at a pressure P. And we are compressing that gas. We are compressing that gas. So pressure will increase during the compression. Pressure will increases. Understand? And value will decreases. Understand? Pressure is increased by dP value and volume is decreased by dV. Once we go for the last slide. Right. Let V is the volume of the gas enclosed in the cylinder and P is the pressure of gas when volume is V. Okay. Now let the pressure is increased to P plus dP. How the pressure will increase in a cylinder? If we compress the gas, then the pressure will increase. In compression, what will happen? Volume will decreases. So volume is decreased from V to V minus dV. Understand? And the pressure is increased from P to P plus dP. Understand? So what is the increase in pressure? Increase in pressure is equal to final pressure minus initial pressure. What is the final pressure? P plus dP. What is the initial pressure? P. So P plus dP minus P. Plus P minus P will be gets cancelled. Understand? Okay. The increase in pressure is dB. Now the decrease in volume is nothing but a final value minus initial value. What is the initial value? V minus dV. V minus dV. And what is the original value? Capital V. So decrease in volume is equal to final value minus initial value. V minus dV. V minus dV minus V. If we simplify it, plus V will be gets cancels with minus V. So we will get decrease in value is dV. Actually, it is a minus. Here we are representing the term decrease. So decrease is nothing but a negative value. Okay. Decrease in value. Indirectly, we are showing that value is decreased. So we will get a negative quantity minus dV. Understand? This volumetric strain. What is meant by volumetric strain? Volumetric strain is nothing but decrease in volume by original volume, or change in volume by original volume. Decrease in volume or change in volume is equal to minus dV. Okay, original volume is V. So volumetric strain is equal to minus dV by V. In strength of materials also we can get this strain. What is meant by strain? Change in length by original length. Change in length by original length is equal to strain. But here we are representing the volumetric strain. That is why we are considering the terms volume. So decrease in volume or change in volume by original value. Change in volume is minus dV. Original volume is V. So volumetric strain is minus dV by V. Now come for the next slide. Okay. What is the meaning of bulk modulus? Meaning of bulk modulus K. This is nothing but increase. It is the ratio of increase in pressure to the volumetric strain. Increase in pressure is nothing but dP, and the volumetric strain is equal to minus dV by V. If we simplify it, we will get dP by V and dP by V into V. Understand? This is the expression for bulk modulus. This is a K represents with K. Understand? Here one hint. Let us say the one hint. How to remember the symbol for bulk modulus. If you read this term bulk, if you read this term bulk, in bulk term there is a K. Okay, bulk term there is a K. So you can put capital K is equal to bulk modulus, that is equal to increase of pressure by volumetric strain. Understand? Compressibility is nothing but reciprocal of bulk modulus. Reciprocal of bulk modulus. In other words, we can say compressibility is the ratio of volumetric strain to increase of pressure. Volumetric strain to increase of pressure. So dV by V will come. dV by minus dV by V by dP will come. So we can write it as a 1 by K. This is a simple information regarding compressibility and bulk modulus. And go for the next slide. Surface tension and capillarity. Okay, what is meant by surface tension? In I think in the 9th standard you studied this. If you see the rain, understand how water dews or rain dews will fall from the sky to earth. If you see the structure of that water droplet, we will find it like a small globe structure, a small bubble structure, okay, which is in a rounded shape. Understand how this water in a dews form, that too in a circular form, is falling from sky or clouds to earth, means because of the tension, surface tension. Understand? I'm not saying the secrecy of rain. Understand? I am saying the structure of water dews. Understand? Because of the surface tension. Okay, surface tension is defined as the tensile force acting on the surface of a liquid in contact with a gas or on the surface between the two immiscible liquids, such that the contact behaves like a membrane under tension. Okay. Once again, we will read. Surface tension is defined as the tensile force acting on the surface of a liquid in contact with a gas or on the surface between two immiscible liquids, such that the contact surface behaves like a membrane under tension. Surface tension is created due to the unbalanced cohesive forces acting on the liquid molecules at the fluid surface. Okay. Surface tension is created due to the unbalanced cohesive forces. Understand? Cohesive force and adhesive force. These are the two important forces of the fluid properties. Okay, cohesive force means the forces between the molecules of same liquid. Same liquid. And adhesive forces means the molecular attractional forces between the molecules and other surface, molecules of the other surface. This is called adhesive surface. Okay, those liquids whose cohesive forces are very much higher, they won't stick to the surface. Understand? They cannot wet the surface in which that liquid is in contact. Mercury is the best example for a higher value of cohesive forces. Okay. Whereas other molecules, water, kerosene, petrol, diesel, coconut oil, and this type of liquids will have adhesive forces. That is why once if we pour these oils on a ground or a containers, this will wet the surfaces. Okay, that is a reason behind this nature. Okay, surface tension is created due to the unbalanced cohesive forces acting on the liquid molecules at the fluid surface. Molecules in the interior of the fluid mass are surrounded by molecules are attracted to each other equally. Let us understand this point. Molecules in interior of the fluid mass are surrounded by the molecules that are attracted to each other equally because liquid substance is containing of large number of molecules. Understand? Each molecule is surrounded by um, other molecules of same liquid. So each molecule will experience this tensile force attraction from and each other very equally. However, the molecules along the surface are subjected to a net force towards the interior. If you want to understand this, let us go for the next slide by completing this point. The apparent physical consequence of this unbalanced force along the surface is to create a hypothetical skin or membrane. This physical sequence of unbalanced forces will form or create one hypothetical skin that is nothing but one membrane. This will act as invisible veil. Okay, this invisible veil or hypothetical skin or membrane will always lie in tension because of this tensile force. Okay, and come for the next slide. A tensile force may be considered to be acting on the plane of the surface along any line in the surface. The intensity of the molecular attraction per length along the line of the surface is called surface tension. Simply, tensile force act per unit length is nothing but a surface tension. This surface tension is denoted by the Greek letter sigma, and its unit is per meter because this is a force per length. Unit for force is Newton and unit for length is meter. Okay, concentrate on this figure. See, one molecule is submerged in the liquid. Understand? So this molecule is experiencing same molecular attraction from the other molecules which attracted by the other molecules. And these cohesive forces are equally balanced. But whereas molecule is on the surface, here there is an unbalanced cohesive force. This force is balanced by this force. Understand? But vertical, this inclined arrow marks showing certain cohesive forces. These two forces are not balanced. Understand? So unbalanced cohesive forces are resulting. Understand? This unbalanced cohesive forces here, the molecules in the interior of the fluid are surrounded by molecules. Where the molecules along the surface are subjected to net force towards the interior. Understand? There is a net force, or unbalanced force is there. The apparent physical consequence of this unbalanced force along the surface is to create a hypothetical skin or membrane because of this unbalanced cohesive forces, it forms a hypothetical skin over the liquid or over the molecules that will act as a membrane, that will act as a veil, okay, due to the surface tension. That force will act along this length of the liquid. Tensile force is acting along the liquid. This tensile force, how this tensile force is resulting? Because of the unbalanced cohesive forces. This is the simple information regarding the surface tension. Here, surface tension on a liquid droplet and a bubble. So bubble, liquid droplet in a rainy season, or if you pour the water from top to bottom, water will flows. If you observe it, we may find certain spherical droplets. Spherical droplets in the form of spherical droplets, water will be fall. Okay. And bubble is nothing but soap bubble. We can see the soap bubble. Kids are also playing certain instruments which forms the soap bubble. Understand? We open the one container cap and put it in the soap water, and if we um, if we flush what the air, what will happen? A soap bubble will form. Understand? If we forcefully, if we made to issue air, understand? This air will flow through the is thin water, soap water layer, and it forms one bubble. Every day we may see these water droplets and soap bubble in our houses. Understand? The formation of that circular bubble droplets and the bubbles indirectly presenting one technical concept, that is because of the surface tension. Okay, here we are considering liquid droplet. This is the liquid droplet, and this is the half bubble. Okay, consider a small spherical droplet of a liquid of radius r on the entire surface of the droplet. Okay, here we are considering one droplet. Okay, its radius is capital R. On the entire surface of the droplet, the tensile force due to surface tension will be acting. So we are considering half or semi-spherical or hemispherical droplet. Enter, this is the circumference. Okay, I'm moving the cursor along the circumference. Tensile force is acting. Okay, why if R is the radius of the this droplet, what is the circumferential length? Pi d or 2 pi r. Okay, tensile force is sigma. Sorry, surface tension is acting along the circumference. So tensile force is equal to surface tension into length 2 pi r. If surface tension is equal to tensile force by length, understand? Sigma is equal to tensile force by length. Then cross multiplication, tensile force is equal to surface tension into length 2 pi r. So this 2 pi r sigma force is acting along the entire circumference. Understand? Similarly, there is a atmospheric pressure force will also act inside the bubble in opposite direction, because one force is acting in this direction and pressure force is acting in this direction. Tensile force is acting away from the circumference and the pressure force is acting in towards the center. Understand? In this way, these two forces will be balanced. Understand? Here, pressure force is represented with the red color, and tensile force is represented with black arrows. Consider a small spherical droplet of a liquid of radius r on the entire surface of the droplet. The tensile force due to surface tension will be acting. Here, let sigma is equal to surface tension of the liquid, and delta p delta p is intensity of pressure inside the droplet in excess of outside intensity. Okay, because outside intensity of pressure is more because of that whole pressure differential. Pressure will act from higher level to lower level. Understand? And R is the radius of the droplet. Let the droplet is cut it into two halves. The surface, the forces acting on one half will be, let's see the next slide. There are two forces. The tensile force due to surface tension acting around the circumference of the cut portion as shown in the figure. Okay, this is the figure already we discussed. This is nothing but the force into length or circumference. Circumference is 2 pi r and the pressure force acting towards into the droplet. What is its area? Pi by 4 d square. Pi by 4 d square. So pi by 4 d square and d is nothing but 2r. If we calculate it, we will get 4r square. Pi by 4 into 4r square. 4 will be gets cancels. What will be remainder? 5r square. Okay, pi r square. Increase of force on the area pi by 4 d square. Nothing but delta p into pi r square. This is the pressure force acting on it. Okay. Next for equilibrium. For equilibrium, these forces will be in equilibrium conditions. These forces will be equivalent opposite under equilibrium conditions. So that droplet tensile force is equal to pressure force. Tensile force is equal to pressure force. Okay. In 2 pi r into sigma s is equal to pi r square into delta p pressure difference. Okay, pi gets cancelled, r gets cancelled. So what are the reminders? 2 sigma s is equal to delta p. This is nothing but a pressure difference. Pressure difference. What is the pressure difference? Inner pressure minus outer pressure. Pi minus P naught. This is equal to 2 sigma. 2 sigma. Here we will be the R. By the cross multiplication, we will send to the left side of the equation. So we will get Pi minus P naught is equal to sigma 2 sigma S by R. 2 sigma S by R. Generally, dimension of that bubble will be expressed in a diameter. Okay, R is nothing but d by 2. R is nothing but d by 2. So in next step, what we can write? Pi minus P naught is equal to 2 by sigma S by d into 2. 2 into 2, 4. 4 sigma by d. We will get 4 sigma by d. The relationship between pressure force and surface tension and diameter for a droplet is equal to 4 sigma d, 4 sigma by d. Remember it in problems. We will come back to this slide. Okay, for bubble, once again, go back to this. Okay, this is the bubble. Here, here we are getting 2 pi r into 2s. This is a droplet. This is a droplet. Understand? This is a droplet, and this is the bubble. So bubble. For this bubble, one thing here. Surface tension is 2 into 2 pi r sigma s. 2 into 2 pi r. That means 4 pi r sigma s. Here, this is a solid half structure of the liquid. That means this is the entire liquid mass is there. Understand? A water droplet is cutting on one surface. Understand? But whereas being it is a bubble, this is the hollow structure. This is the hollow structure. This water bubble will have inner surface and as well as outer surface. This will have no inner surface. It will have only one surface. Understand? Because it is a entirely a fluid or a liquid droplet. Being it is a bubble. Inside there is a air presented. Outside air is a presented. Inside there is a circumference. Outside there is a circumference. That is why uh, double to the uh, surface tension will act. Understand? 2 times of the surface tension will act on the bubble. So 2 into 2 pi r sigma s. And same, pressure is same. Pressure is same. Pi by 4 d square into delta p. Same it will act. Okay. For a bubble, 2 into 2 pi r sigma s. 2 into 2 pi r sigma s is equal to pi r square. Understand? Pi gets cancelled, r and square gets cancelled. So what will be the remainder? 4 sigma s is equal to delta p into r. Delta p into r. Delta p is nothing but pressure difference. Pi minus P naught. Pi minus P naught is equal to 4 sigma by r. 4 sigma by r. Understand? If we want to express this relationship in diameters, you can put r is equal to d by 2. Okay. In next step, what we can write 4 sigma by d into 2. So 4 into 2, 8. 8 sigma by r. So what we can write directly for a water bubble. For water bubble, pressure difference is 8 sigma by d. For droplet, pressure difference is equal to 4 sigma by d. Are you following? Next one slide. Let us see one problem. Read the problem. Anyone? Anyone, please read the problem.
Find the surface tension in a soap bubble of 40 mm diameter when the inside pressure is 2.5 Newton per meter square above the atmospheric pressure.
Okay, right. So in this problem, what is given data? Soap bubble is a thing. Given criteria, the given thing is a soap bubble, and its diameter given, and the inside pressure 2.5 Newton per meter square above the atmosphere given. What is asking? He is asking us to calculate the surface tension. Okay, first to write down the diameter of the bubble. D is equal to 40 mm. Convert it into meter. So 40 into 10 to the power of minus 3. Okay, 40 into 10 to the power of minus 3. And pressure in excess of the outside, given pressure 2.5 Newton per meter square. So for soap bubble, pressure difference P is equal to 8 sigma by D. 8 sigma by D. Okay. Lastly, we discussed what is the pressure value 2.5 is equal to 8 into sigma by diameter D 40 into 10 to the power of minus 3. If you simplify it, we will get 0.0125 Newton per meter length. Okay, this is simple information. For soap bubble, pressure difference is equal to 8 sigma by D. And let us see another problem. The pressure outside of the droplet of water. The pressure outside of the droplet of water of diameter 0.4 mm is 10.32 Newton per centimeter square. Atmospheric pressure. Calculate the pressure within the droplet if surface tension is given by 0.0725 Newton per meter of water. Okay.
Bluetooth.
Okay. What is the thing? Given thing.
Bluetooth on this.
Given thing. What is the given thing? The pressure outside of the droplet of water. He mentioned droplet. Okay, droplet of water. Okay, droplet. For a droplet, what is the pressure difference expression? P is equal to 4 sigma by D. P is equal to 4 sigma by D. Okay. So what is the diameter of the droplet? 0.04 mm given. Pressure outside of the droplet 10.32 Newton per centimeter square. Surface tension given in the problem 0. 1 minute. Hello. Sir, good morning, sir. Class jarugutundi sir. Second year civil ki class jarugutundi sir. Yes, sir. సార్ నేను ఇక్కడ వీడియోస్ అయితే అప్లోడ్ చేయలేదు సార్. అటెండెన్స్ మనం స్టూడెంట్ అటెండెన్స్ అవన్నీ డౌన్లోడ్స్ మెయిల్లో పెట్టుకుంటున్నాను సార్. మీటింగ్ అటెండెన్స్ సార్. వీడియోస్ కూడా ఇక్కడ రికార్డ్ అవుతున్నాయి సార్. ఇక మామూలుగా మన కాన్ఫరెన్స్వి దాంట్లో ఇప్పుడు క్లాస్ చెప్తున్నాను సార్. అటెండెన్స్ అయిపోయిన తర్వాత నేను అటెండెన్స్ మీటింగ్ అటెండెన్స్ డౌన్ సార్. అదే సార్ మీరు పెట్టిన మెసేజ్ చూశాను సార్ నేను. అయితే ఇది ఎలా చేయాలో నాకు తెలియక ఆగాను సార్. అదే సరే సార్. విషయం ఏంటంటే సార్ నేను ఫోన్ మార్చాను సార్. అందువల్ల మీ నేమ్ డిస్ప్లే కాలేదు సార్. అంటే ఎవ్రీడే ఈవినింగ్ క్లాస్ అయిపోయినాక వినోద్కి ఆఫీస్ వినోద్కి ఇన్ఫర్మేషన్ ఇస్తున్నాం సార్. సార్ ఓ సార్. సార్ సరే సార్. ఓకే సార్. ఓకే సార్. సరే సరే సార్. ఓకే సార్. సార్ సరే. ఓకే సార్. సరే సార్. సరే సార్. థ్యాంక్ యూ సార్. Hello. What is the data given in the problem? Pressure outside of the droplet of water diameter 0.4 mm is 10.32 Newton per centimeter square. Atmospheric pressure. And calculate the pressure within the droplet if surface tension is given as 0.0725 Newton per meter of water. The diameter of the droplet given D is equal to 0.04 mm. That is equal to 0.4 10 to the power minus 3. And the pressure outside of the droplet, that is called 10.32 Newton per centimeter square. Convert it into meters by putting 1 centimeter is equal to the power of minus 2. Okay. We will get a 10 to the power of minus square. If minus 4, you bring it to the numerator, we will put a positive sign. 10.32 into 10 to the power of 4. Okay. Surface tension. Given value sigma is equal to 0.0725 Newton per meter. And now next, the pressure inside the droplet. The pressure inside the droplet in excess of outside pressure is given by P is equal to 4 sigma by D. That is equal to 4 into 0.0725 by 0.4 into 10 to the power minus 3. That is the diameter. Okay, once we simplify it, we will get 7250 by 10 to the power 4. We will get 0.725 Newton per centimeter square. This is the pressure we got. Okay, what is the thing he has to calculate the pressure within the droplet. If you want to calculate the pressure inside the droplet, we have to consider the pressure outside of the droplet also. Okay, 10.32. This 10.32 is the outside pressure. Okay, and what is the inside pressure? 0.725. What is the total pressure? 0.725 plus 10.32. We will get 11.045 Newton per centimeter square. This is the given data. This is the required data. And go for the next slide. Capillarity. Capillarity. What is meant by capillarity? Capillarity is defined as a phenomena of rise or fall of a liquid surface in a small tube relative to the adjacent general level of liquid within the tube is held vertically in the liquid. It is defined as the phenomena of rise or fall of a liquid surface in a small tube relatively to the adjacent general level of liquid when the tube is held vertically in the liquid. Okay, the rise of liquid surface is known as capillary rise, while the fall of the liquid surface is known as capillary depression. Okay, the attraction or adhesion between the wall of the tube and the liquid molecule is strong enough to overcome the mutual attraction or cohesion of the molecules as pull them up the wall. Okay, adhesion portion and cohesion portion. So adhesion and cohesion is the two important parameters which are acting or which are coming in the concept of capillarity. The attraction, what type of attraction it is? Adhesion. The attraction due to adhesion force between the wall and the tube and the liquid molecules. Liquid molecules is strong enough to overcome the mutual attraction. Mutual attraction means attraction of the same molecules of same liquid of the molecules and pull them up the wall. Because of this only the water level is moving upside and water level is moving downside. Hence the liquid is said to be wet the solid surface. It is expressed in terms of centimeter or mm of liquid. Its value depends upon the specific weight of the liquid, diameter of the tube, and the surface tension of the liquid. It is expressed in terms of centimeter of liquid. Its value depends upon the specific weight of the liquid and diameter of the tube and the surface tension of the liquid. Go for the another one, surface tension and capillarity. Consider a glass tube of small diameter D opened at both sides and inserted in a liquid, say water. So this is one water content in this beaker or a vessel. A small glass tube with two openings is dipped into the or inserted into a liquid. So what will happen? Simply water level will rises up in the tube. Water will be rises up in the tube. See, this water level rises at a height of h from the outside water surface. Outside water surface, and this is a structure of the inside water or raised water. Understand? Because on the water, atmospheric pressure will act, so it forms a curved structure, concave structure. Understand? So along this surface tension will act. Understand? If you observe, there is a line of action of surface tension and surface of the tube, we will get a small angle theta. Understand? Let h is the height of the liquid in the tube. Let h is the height of the liquid in the tube. Under the state of equilibrium, the weight of the liquid of h, height h, is balanced by the force at the surface of the liquid in the tube. But the force at the surface of the liquid in the tube is due to surface tension. But the force at the surface of the liquid in the tube is due to surface tension. Okay. Come for the next slide. Expression for capillary rise. Let sigma is the surface tension of liquid, and theta is the angle of contact between the liquid and the glass tube. The weight of the liquid of height h in the tube is equal to, what is the expression for the weight? W is equal to mg. Okay, W is equal to mg. G same. In case of mass, we are writing this much terms. Okay. What is the relationship between density and mass? Density and mass is nothing equal to, density is equal to mass by value. Okay, value is nothing but area into height. Area into height is nothing but value. Value into density is equal to mass, because density is equal to mass by value. Cross multiplication, m is equal to value into density. Understand? So what is the area of the tube? Pi by 4 d square. H as usual. Rho g as usual. Okay. The weight of the liquid of height in h meters is pi by 4 d square h rho g. Pi by 4 d square h rho g. Okay. Where density is the density of liquid. Vertical component of surface tensile force is equal to sigma into circumference. Vertical component cos theta, and what is the circumference? Pi d. Sigma pi d cos theta. This is the surface tensile force, vertical component. For equilibrium, these two forces are equal, because force due to the weight of the liquid is equal to the tensile force. Understand? This is the force due to its weight of the liquid, and this is the force due to surface tension. For equilibrium, these two are equal. So if we solve this, we will get h is equal to 4 sigma cos theta by rho CD. Expression for capillary rise is 4 sigma cos theta by rho CD. That is the thing we have to remember. The value of theta between water and clean glass tube. Value of theta between water and clean glass tube is approximately equal to 0, and hence cos theta is equal to 0, because cos 0 is equal to 1. Therefore, h is equal to 4 sigma into 1 by rho CD. We will get h is equal to 4 sigma by rho CD. Contact angle depends on both of the liquid. Contact angle theta depends both on liquid and the solid. Okay. If theta is less than 90, the liquid is said to be wet the solid. However, if theta is greater than 90, the liquid is repelled by the solid, and it will not rises, and it will not wet the surface. For example, water wet the glass but not the wax. Mercury, on the other hand, does not wet the glass. This is the thing. And another expression, capillarity. Expression for capillary fall. See, in two beakers, we are taking water in one beaker or one vessel, and mercury in another vessel. Understand? In in both beakers, we are dipping or inserting two glass tubes, which has both openings, the top side and bottom side. Understand? One is inserted in water. So what happened? Water level rises up. Water level rises up, and this is greater than the surface level, which is greater than 0. Okay, and whereas in mercury, if you insert the glass tube in mercury, what will happen? This mercury level fall below the outside level. Understand? This is H is less than 0. H is less than 0. Come for this expression for capillary fall. If the glass tube is dipped in mercury, the level of mercury in the tube wall will be lower than the general level of the outside liquid. If the glass tube is dipped in mercury, the level of mercury in the tube will be lower than the general level of the outside of the liquid, as shown in figure. Okay. See, this is the fall of liquid level. This is one glass tube, and this is the mercury level. And then here we are getting the surface of liquid inside the tube. Okay, that H is the height of depression, which is the height of depression. Okay, then the equilibrium, the two forces acting on the mercury inside the tube. The first one is due to the surface tension acting in the downward direction, and is equal to sigma pi d cos theta, and it is equal to sigma pi d cos theta. Second force is due to hydrostatic force. Second force is due to hydrostatic force acting upward, and is equal to the intensity of pressure at a depth h, okay, into area. From bottom side, pressure force is acting, and from top side, surface tension is acting. Force due to surface tension. Okay, come for the next slide. Expression for capillary fall. For equilibrium, this pressure force is equal to tensile force. This is the pressure force, and this is the tensile force. Pressure force is P into pi by 4 d square. P is equal to rho g h. P is equal to rho g h from hydrostatic law. Okay, so what is the final expression? Rho g h into pi by 4 d square. This is the pressure force. And sigma pi d cos theta. This is the tensile force. Tensile force is equal to the pressure force. Okay, so if we simplify it, we will get H is equal to 4 sigma cos theta by rho gd. H is equal to 4 sigma cos theta by rho gd. Pi gets cancelled, dd gets cancelled. Okay, this H is equal to this 4 by cross multiplication. It will come to the numerator. 4 into sigma. 4 into sigma by rho g d. Cos theta as usual. Therefore, H is equal to sigma cos theta by rho g d. The value of theta for mercury and glass tube is 128. The value of theta for mercury and glass tube is 128 degrees. If we substitute 128 degrees in theta place, we will get a negative value for this H, because this is the depression or decrement or decrease or fall value, which is measured from surface to the downward direction point. take one problem. Read the problem, anyone please.
Calculate the capillary rise in a glass tube of 2.5 millimeter diameter when immersed vertically in A, water, and B, mercury. Take the surface tension sigma is equal to 0.0725 Newton per meter for water and sigma is equal to 0.52 Newton per meter for mercury in contact with air. The specific gravity for mercury is given as 13.6 and angle of contact is equal to 130 degrees.
Yes, 130 degrees. What is the data given? The problem diameter of the tube given. Okay, diameter of the tube how much? 2.5 mm. Converted it into meters. 2.5 into 10 to the power of -3. Surface tension sigma for water is equal to 0.0725 Newton per meter. Sigma for mercury, that is equal to 0.52 Newton per meter. Specific gravity of mercury, that is equal to 13.6. 13.6. And next slide. Density is equal to 13.6 into 1000. Here we have to get one doubt. Sir, is a standard value mercury means? Yes, this is the standard value of for mercury. Standard value of specific gravity for mercury as 13.6. Understand? Here density of the mercury not given. Density of mercury not given. But we can calculate with help of specific gravity. What is the meaning of specific gravity? This is the meaning. Specific gravity of the mercury is equal to density of mercury by density of water in general formula. Specific gravity of mercury is equal to density of mercury by density of water. Now density of mercury is equal to specific gravity of mercury into density of water. Otherwise, specific gravity S is equal to density of mercury L by density of water rho W. Rho L is equal to S into rho W. Rho W is nothing but the density of water. S means specific gravity. Specific gravity, okay. Specific gravity is equal to 13.6 and density of water is equal to 1000. 13.6 into 1000. Okay, this is the density of the mercury. Capillary rise for water is equal to 0. And what is the expression? H is equal to 4 sigma by rho ZD. Rho ZD. Understand? 4. Substitute the value of sigma and the rho value, G value, and the diameter of the tube. We calculate it, we will get 0.0118 meter. Understand? If you want to express it in centimeters, multiply that value into 100. So we will get 1.18 centimeter. For mercury, angle of contact between the glass tube is 130, given in the problem. Okay. If value is not given, we can take it as 128 degrees. 128 degrees. So for mercury, capillary fall or rise, H is equal to 4 sigma cos theta by rho ZD. 4 substitute the value and sigma 0.52 cos 130 rho sigma 13.6 into 1000 Z 9.81 diameter D 2.5 into 10 to the power of -3. Being cos value is 130 degrees, we will get a negative value because from a trigonometry in second quadrant cos theta is negative. That is why we are getting negative value. And also if H is equal to minus 0.4 or minus 0.004, It indicates depression or a fall from the surface. This is the thing. They are mentioning the negative sign indicates the capillary depression. And come for the second problem. Find out the minimum size of the glass tube that can be used to measure the water level if the capillary rise in the tube is to be restricted to 2 mm. Consider surface tension of water in contact with air as 0.073575 Newton per meter. 0.073575 Newton meter. Okay, what is the data given in the problem? H is equal to 2.2 meter. Converted it into meters. 2 into 10 to the power minus 3. What is the surface tension? Sigma is equal to 0.073575 Newton per meter. Let the diameter of the tube is D. The angle of theta for water is 0. Density of water is 1000. Okay, what is the expression for capillary rise? H is equal to 4 sigma by rho CD. 4 sigma by rho CD. Here H value given 2 into 2 mm. It is restricted to 2 mm. Understand? And sigma value also given. But he is asking us to calculate the diameter of the glass tube D. So if we solve this expression for D, we will get the diameter of the glass tube as 0.015 meter or 1.5 centimeter. This is the minimum diameter. The minimum diameter of the tube should be 1.5 centimeter. This is the simple information regarding the surface tension and capillarity. Okay, in next class we will meet you again. Okay. Thank you very much to you all. Now you can leave.
Sir, I have a doubt.
Okay.
Sir, should we write notes, sir? Notes for this chapter, sir.
Hello?
Sir, notes for this chapter, sir.
Hello? Any doubt?
Sir, should we write notes regarding this chapter, sir?
I will send the PDF material. Okay?
Okay, sir. From 13th onwards, they are saying mid-exam, sir. So that for preparation we want.
Yes, sir. You go through that slides also. Okay?
Okay.
Right.
Thank you.
Thank you. Right. Thank you. You can leave.